Hello and welcome. I'm Feder Gaumans from Software for Chemistry and Materials. Today I would like to share with you some pointers and ideas which will hopefully help you find transition states more efficiently. There are two very important points to consider. One is that you make sure that you get a geometry which is as close as it can be to the transition state itself. So that is the geometry that is a maximum along the reaction coordinate, taking you from the reactant valley to the product valley, and is a minimum in all the other directions. That also brings me to the second important point, which is in order to find that first order saddle point, maximum in one direction, minimum in all the other directions, is that we need to help the optimizer with a good description of the curvature of the potential energy surface around that transition region. In particular, we like to provide the optimizer with a good description of the lowest eigenmode of the Hessian, the second derivative, with respect to the nuclear coordinates. And so there's several ways that you could help it. One is by providing it with a partial Hessian, so only calculating the second derivatives of the atoms which are most involved in the transition itself. What I'll demonstrate today is also how you can use a low-level Hessian. So when we calculate a transition state with ADF, or molecular density functional theory code, we could use a Hessian from density functional base tight binding, which is an approximation to density functional theory by using pre-calculated matrix elements and nearest neighbors and minimal basis set approximation. Also very specific to ADF and the Amsterdam Modeling Suite is the option to explicitly define a reaction coordinate along which the optimizer should search for a maximum. This is called TSRC, transition state reaction coordinate. So if you know, these are the bonds which are going to be broken and formed, these are the angles which are going to be opened up, then you can define one coordinate which is a composite of all these things happening at the same time in a transition state. So if you have a very complex reaction where a lot of things are happening at the same time, this can still be done, but might be a bit more difficult to set up than just calculating the Hessian at a lower level or calculating a partial Hessian. Once you've found your transition state in ADF, there's also the option to consider just checking whether it's a transition state by not calculating the Hessian fully, and this is called transition state point characterization, and this will check whether you have one negative eigenmode or one imaginary frequency only, which is necessary and sufficient condition for a transition state. Good. Okay, so let's now discuss a few options which might help you to get as close as you can be to the geometry of the state that takes you from reactant to product, the transition state. First and foremost, you may want to consider if people have done similar things, so look in the literature for or ask your colleagues whether they've studied similar types of reactions, and that will be a very good starting point for you to start finding the geometry that takes you indeed from reactant to product. In particular, you can just import coordinates from a paper, we'll do that later on, and then use that as a starting point. And then maybe once you have already found a transition state or somebody else and you just want to modify some ligands, what you can also do is keep the atoms involved in the transition fixed while you optimize the other parts of the system. And so that is the tips here. So use a previous transition state for a similar system and then consider first doing a constrained or a partial optimization. If we have the reactant and the product states, we can also use climbing image notch elastic band, and you can do that all the way, so let the climbing image climb all the way up to the transition state. Usually it can be more efficient to use notch elastic band as a very quick and dirty way to find the reaction pathway and let the climbing image climb up a little bit, and then extract that as a good geometry using Hessian-based Surth methods with a good Hessian. So there could be a lower level Hessian like the tight binding Hessian. What you could also do is scan the potential energy surface. So if we have the reactant state, we could define a composite scan coordinate, so just like we could with the TSRC, where we say, okay, we are going to see what happens when we change this distance or this angle, keep it fixed but optimize all the other things. And so that can be a very quick and efficient way to sort of quickly scan the potential energy surface landscape, extract the highest point, and then do a transition state search from that. Usually, again, you want to use quick and dirty convergence criteria because we're not really interested in the entire path, at least not to converge that as strongly as we can. We do want to converge at transition states as tightly as is necessary. One further tip, so sometimes it can be more effective, or it can be easier to scan from the product side. So if we have the product side, we can also do a scan that drags us up to the transition state region from the product to the reactant side. Okay, so now let's apply a few of these tips and tricks to a very simple catalytic reaction, which has been studied extensively by the Bickelhout group, namely oxidative addition, CH activation, methane, oxidative addition to palladium model catalyst. And the very most basic system that we could study is just palladium with 2 phosphine ligands. So let us build that. There's various ways that we could do that. So let's draw 3 atoms roughly in a line and add hydrogen atoms with Ctrl E to the end, and substitute that middle atom for a palladium. So right click on that, again select the carbon atoms, right click on that and change it into a phosphor. You will see that the phosphor hydrogen bonds have been adjusted based on atomic radii and as well as the palladium phosphor bond. You can use the slider to modify the distance or just type in a number here. In this case, we'll do a quick pre-optimization using XTB. Right click on this little cogwheel here, which defaults to a UFF optimization, to switch to XTB. And the first thing that you will notice is contraction of the palladium phosphorus bond and slightly twisting here. So we measure the angle here. You can see actually this is much more bent than the preferred DFT structure. So something to bear in mind, that the DFTB may or may not be a good representation of your system, so also when you think about calculating a Hessian using that method. Good, so this is then at the DFTB level our resting state for the catalyst. Now we want to add methane to it, and so I could just search for CH4 and that will be added then into my drawing box. If I right click on one of the atoms, I can drag it up and I can rotate the system and drag it a little bit like so. If I left click on one of these selected atoms, I could rotate the system. Alright, so again do a little bit pre-optimization using XCB. That is going to be our resting state with the methane having a coordination with the central palladium atom. Alright, I think that is enough for now because I actually want to do a proper optimization, so I'll switch to DFTB and make sure that the XTB Hamiltonian is selected. I would also like the frequencies in case I want to do a assessment of the free energy of activation, the Gibbs free energy, which also includes enthalpic and entropic contribution from these frequencies. And let me save this as palladium CH4 reactant, and let me then run this job. And whilst that is running, we set up the product state. In that case, this bond here is broken, so delete that, move that hydrogen atom in that direction, drag the methyl group drag it around, rotate it a little bit, and then just add a bond here using Control Command L. Same thing here, Control L. And if I wanted to do a optimization of just part of the system, doing a pre-optimization, I could select those atoms and then again do a pre-optimization of just part of the system. Meanwhile, I'm interrupted. This is why it's advisable to do a actual new input if you start a new system. So in this case I will say no, because I'm working on the product side of things. Okay, let's quit this for now and save this as my product state. And also run that. Okay, then the two tips that I mentioned, if we don't have a good starting point for a transition state yet, is to do a potential energy surface scan, and the other one is doing NEB. For the NEB, it's advisable to have an optimized reactant and product, so we'll wait for that. But in the meantime, I could already set up my scan coordinate from the reactant state. Remember, sometimes it's actually easier to scan from the product state than it is from the reactant state. So if you're not successful finding a good pathway when setting up a scan, that is an option you could try. Okay, so now I do want to get the updated geometry. I will untick frequency and switch to potential energy surface scan, and I want to set up a scan whereby I break this bond and form the palladium carbon bond. So I will go to the details panel. I will update in the meantime product geometry, which will be helpful to define the endpoint for the potential energy surface scan. I will go to the details of the PES scan, and I will want to increase this bond. So select those and click on distance, and in fact I will measure here how far what the endpoint should be, so around 2.32 angstrom. And at the same time I want to start forming this palladium carbon bond here, so I add that as another scan coordinate, and I want to decrease that from 3.03 to 2.044. And if I don't do anything at all, it will do a two-dimensional scan, so it will have 10 by 10 points, but I want to scan the bond breaking and the bond formation simultaneously, so I will assign one scan coordinate that does a composite scan of both these two bond breaking and bond formation events. I want to do pretty slack convergence, so I recommend a factor of 5 or a factor of 10 less stringent, so I'll do a factor of 10 here. Okay, let's save this as a different job, call that scan, and run that job. And while that job is running, we will set up our NEB calculation. For that we go back to this input window here, and we will switch off frequencies, change task to NEB, and again use this little triangle here to go to the details of the NEB panel. By default it will climb to the highest image on the transition state, and it will spawn a climbing image instantaneously. I would suggest doing that a little bit later, so 0.01 heart rate per bore is a good starting point. Interpolation in internal coordinates is almost always a good idea. The default spring value of 1 heart rate per bore squared, or if you prefer electron volt per angstrom squared, so you get something on the order of 100. That is usually pretty decent. Number of images, something like 7 or so is advisable. If you have a very complex reaction where you have multiple intermediate states, you might make that a little bit larger. And now we just need to define the initial and the final state. So for the initial, let's in this case use the current molecule, and for the final system we want to create a new molecule for which we import the reactant state. So we do import coordinates, and then we find here our results directory for the reactant state and select the RKF file. And so we can see now this is our first molecule, that is the second molecule, and we want to essentially map all these atoms one-on-one, create springs between them, and then optimize the entire much elastic band. Don't forget to save this as a different file, so call it NEB, and I will also run this job, which means it will be in the queue waiting for our scan job to finish. So again, when the calculations are finished, the graphical user interface will prompt us to read in the new coordinates. In this case it's not necessary. And let's just have a look at what has happened. So we go to SCM movie, and by default, if the job is finished, the scan it will only show converged points. Okay, so this looks like a good transition state coordinate. Let's see what happened with the NEB. So we'll open that one up. Again, SCM movie. And there, let's see what happens here. Remember, in this case we started from the product side, so this is the mirror image of this reaction profile, if you will. And then in this case this would be our transition state candidate, and as you can see that both are pretty similar, also similar in energy. Okay, so now we can take coordinates of either one of them. Let us take those from the test scan. Select everything, press Ctrl C, then I will make a new input window, new input, and in that input window I will just paste these coordinates. There's also an option to save them and then import them as XYZ, but in this case I will just use Ctrl C, Ctrl V. I was calculating this with GFNXDB, and so let me switch to that. And now I want to do a transition state search. I do want to have the frequencies to make sure that we have the transition state, and in order to guide the Hessian based search mechanism we will define the initial Hessian, and so at the DFTB level that's quite cheap, so we can just calculate the Hessian. At the ADF level, as we'll show later on, we can just either import the Hessian from a DFTB calculation, or what we can do is calculate it with a fast engine, which would default to DFTB if you're using ADF. Now we keep the regular convergence criteria, and you also see this option here, characterize potential energy surface point. We could use that if we don't want to do a full frequency calculation, but we want to make sure that we have one negative eigenmode or imaginary frequency. Good. Okay, so let us save this as ch4ts, and run this job. Okay, so let's import the new coordinates, and you see nothing much has happened. So we're pretty close to transition state geometry here, and we want to have a look at spectra, which gives us the infrared spectrum in this case, and now we can verify that we have one and only one imaginary frequency, which in this case is this mode corresponding to the CH bond breaking. Okay, excellent. So we found a transition state. Let's also have a look at the output here. So we go to SCM output, because in 2020 we have a new feature. Here we go to statistical thermal analysis here. Well, we get the enthalpy and entropy contribution to the free energy, and you will see here noted with a little c that these properties have been calculated using a low vibrational frequency free rotor correction, which was originally developed by Stefan Grimmer. So those are a little bit better suited for systems where you have a lot of low-lying frequencies. Good. Okay, so we found a transition state. Certain that it's really a transition state, but obviously now we want to step it up in terms of accuracy. So now we want to switch from DFTB to ADF to do a molecular DFT calculation. So we here select from the drop down transition state, and for now we will untick the frequencies box. If you have a GGA, you could actually do that quite quickly for a system like this, but I also want to demonstrate here in this input window, detailed geometry optimization, there's an option called characterize best point, which will use the Davidson diagonalization to find the lowest two eigenmodes, and that can be a much quicker way to ascertain that you have one imaginary frequency only, one negative eigenmode. Also in this panel we will define the initial Hessian for our transition state search. You can calculate it at the level of theory, as we did for DFTB. You can calculate it with a fast engine, which would default for ADF to calculating it with DFTB, but in this case we already calculated it, so we will read it in from file. So from file, and then select that from our results section. So CH4TS results, DFTB RKF holds that Hessian. And then we want to use a GGA with dispersion correction. So let's try EBD3 Becker-Johnson. Scalar relativistic is default in 2020, which is good. For a basis set I will choose DZP, which will default actually to triple zeta with polarization for the transition metal. I will leave all the other things default. For accuracy considerations you may consider a larger basis set and better accuracy settings for the density fitting and the integration, as well as considering different exchange correlation functionals. Good. We'll save this job as CH4TS ADF amps. And now I will run this not on my local machine, but I will put it on a remote queue, and I will run that, and you will notice that it has a dependency here, and it will copy that DFTB RKF file to the remote cluster as well. So it will use that Hessian to calculate the transition state on the remote machine. And 16 core machine, it shouldn't take that long. We can actually follow the transition state search as it goes on. You see at the start actually it has pretty far off gradients from where we would want it to be, but surely but steadily enough it will zoom into the transition state for this particular reaction. And let's wait for this to finish, a couple of more steps. Okay, so it's finished. We can read in the new coordinates, and you see transition geometry is pretty similar, but of course the bond distances are slightly different at the DFT level than they are at the DFTB level. I have here a couple of relevant results file locally, and on the remote machine I have the full output files and a few other things that I could transfer over if I wanted to. So the log file is just a very terse summary of the calculation the full output file could be useful for future reference as well. But all the results that you need are on these RKF files. So if you want to rerun a calculation, you could find coordinates. You could restart from the wave function there as well. It has done a transition state characterization. So if I now do spectra, we'll find only 2 lowest modes, and hopefully one of them indeed corresponds to the transition mode here. Good. Okay, so that would be a quick way to ascertain that you have a transition state without actually calculating the full frequencies. So that means that you don't get the full thermodynamic corrections from a characterization like that, but at least you know for sure that you have a transition state. Okay, now let's try something else. Let's just look at what these people have done here in this particular paper. And if we go to their paper and see if we can find their supporting information, and maybe we can find actually coordinates there. There we go. Oops, supporting information, and we click on that. Then we'll find, I think in table 3, the coordinates for the transition states, and we could just copy those coordinates, and let's go back to our transition state input window, delete these here and paste them in here. Now they use slightly different settings for the density functional calculations, but this should probably be a much better starting point than using the DFTB geometry. Now of course we cannot just, we're not certain that we have the same numbering of the atoms here, so if we want to use a DFTB Hessian we actually have to calculate it. So if you remember, that could be done here by choosing calculate with fast engine, defaulting to DFTB in this case. Now if I save this as CH4 TSADF from coords, and so these are the coordinates from this paper, and again let us just transfer that to a remote queue and run it. But the geometry is the same. It took 2 steps less than starting from the DFTB geometry, so the DFTB transition state in this case is not that bad, and using the DFTB Hessian is also a good idea. Now let's say I've got a geometry like that, but I want to see what happens if I modify the ligand. Maybe I want to push a little bit more electrons into the transition metal, which would probably make the transition state a little bit earlier. So I can replace this hydrogen atom here by structure, alkyl chain, methyl. So probably that's not going to affect the transition state too much, but maybe I want to do a quick and dirty local optimization of this part of the system. So shift and left click, drag it, and then do GFNXDB just to optimize that part of the system. So we've seen that before, and that is what I'm meant when I mentioned maybe you want to do a local optimization. You can actually do a constrained optimization with ADF as well. So we could select all the other parts. So there's an option, select invert selection, and then you could run a geometry optimization where you fix all the Cartesian coordinates or the relative coordinates of that part of the system. Okay, so I think this is good enough for now, and I will stop this pre-optimization because we do want to find the transition state with ADF in the end. I still keep the task a transition state, use the same density functional approximations, and make sure that we actually calculate the Hessian beforehand with this fast engine. So save this as CH4TS ADF ligand modification, save, and again run this job on the remote machine. So while selecting this job, put it to IV and then run it, and then wait for that job to finish. If you're interested in doing these kind of things, so we have a transition state, we want to modify the ligand, do a local pre-optimization and then run another transition state search. These are the kind of things you could perfectly script to make your lives easier. So if you're interested in that, we have some PLAM script available to get you started. So let us know, and maybe you can be even more efficient in finding more transition states. This job is finished. We can see that it took around 10 steps, or actually 20 steps, and what is happening is mostly involved in this part of the ligand. So we could have done a constrained optimization maybe with a very sloppy ADF calculation. So let me just demonstrate how to do that. So we had that part of the system selected. We could do regular geometry optimization, and then under model, geometry constraints and PESCAN, I will do invert selection, and that will keep all these atoms fixed. So that is one option. Okay, so let's have a look at the log file, and indeed at the end we'll see that a transition state search was successful. So we found a single imaginary frequency, and again we could actually use these coordinates for doing another ligand modification, or if you do a lot of these, Python scripting could definitely be something that would boost your productivity. Okay, so hopefully this video has demonstrated some tips and tricks. So find your reactant products is always useful. Then setting up an NEB to get close to your transition state, or do a potential energy surface scan across the most important mode. Then the second important step is to ensure that you have a good description of the local curvature, in particular the lowest eigenmode. So we could reuse a Hessian from a lower level method or calculate it, specifically in AMS 2020 that's possible directly. We could also define a transition state reaction coordinate. I didn't demonstrate that, but it can be useful for systems where you have a straightforward reaction coordinate. And I didn't discuss yet this partial Hessian, but that will be particularly useful for heterogeneous catalysis, which hopefully will be the topic of a future video demonstration. And finally, I leave you with some questions to consider yourself, which is the accuracy of these type of calculations, particularly if you have ionic systems or you have systems where you have strong bond polarization across your reaction profile. You definitely want to consider including Cosmos solvation, which has gradients available, or you could do single point calculations using the SM12 solvation model. GGAs typically are recommended for speed and accuracy, both for transition metals. Sometimes you want to go to hybrids, but oftentimes that doesn't necessarily give you better energies for transition metal chemistry, and particularly not for activation energies. Meta GGA sometimes can help, and you definitely want to think about basis sets, so triple zeta with polarization or triple zeta with double polarization could be a consideration. This is a 2019 version. We also have double hybrids available, and you will find some pointers on our website for which type of reactions these could be useful. And they're relatively fast, so they're not much more expensive than regular hybrids, although they're single point only. And I already mentioned that currently we have these low eigenmode corrections to the frequencies, which give slightly better thermodynamic functions. Good. This was quite a lengthy video. I do hope it is useful for those of you doing transition state searches. As I mentioned, hopefully we'll do a video in the future on doing similar things for reactions taking place on surfaces. But if you have other suggestions or things you'd like to see demonstrated, please drop us a note or leave us a comment in the video below.